Hello everyone. Today we will begin our exploration of calculus starting with the first unit, limits. This chapter focuses on limits which serves as the foundation of calculus. The concept of limits threads through the entire study of calculus and will be revisited in subsequent topics when we derive derivatives and integrals. So, let's officially begin our journey into AP calculus. And in this chapter on limits, we will cover three main sections. First, what are limits and the concept behind them? Second, how to compute limits. And the third, how to apply limits appropriately once we understand them. We encourage you to leave any questions or thoughts in the video comments section and join the discussion. So, before formally explaining the concept of limits, let's start with a simple example to understand them. For instance, when we're driving on the road, we might see a speed limit sign of 40. Now, consider this. If I'm a highly skilled driver and control my speed at 39, so do you think am I speeding? Clearly not. If I control my speed at 39.9, am I speeding? Still clearly not. And if I take it even further, controlling my speed at 39.999, am I speeding? Obviously, still not speeding. In this scenario, 40 is the limit of the speed. Mathematical limits are very similar to real-life limits. They represent values that we can approach infinitely close, but never actually reach. So let's now explore limits using a function. This function is a rational function. For rational functions, the domain requires that the denominator cannot be zero. So this function is defined only when x is not equal to 1. Therefore, there is an undefined point at x equal to 1, meaning x can never equal to 1. Although x can never actually reach 1, we can study how the function behaves as x approaches 1. So let's take a look at the following table together. So we can find as x approaches 1 when x is 0.75, y is 2.313. When x is 0.9, y is 2.710. And when x is 0.99, y is 2.970. When x is 0.999, x is 2.997. And also from another side, we can find when x is larger than 1 as it becomes 1.25, y is 3.813. And x is 1.1, y is 3.310. And x is 1.01, y is 3.03. And when x is 1.001, y is 3.003. So we can observe that as x approaches 1 from both directions, the value of y steadily close to 3. Hence, we say the limit of the function as x approaches 1, which is 3. Okay. And now let's move on to the mathematical definition of the limit. When x approaches a specific point from both directions and y approaches a fixed value L, we say the limit of the function as x equal to a is L. And we write a notation like this. So here the right arrow, that means x is approaches a. And the limits notation with fx, that means the y's get closer and closer to the L. And this notation can be read as the limit of fx as x approaches 1, which is 3. Okay. So after understanding the concept of limits, let's use an example to deepen our comprehensions. So feel free to pause the video here and think it through before continuing. I'll wait for 5 seconds to give you time to pause. So this question asks us to analyze 3 points, -2, 0, and 3. First, at the point -2, we observe that as x approaches -2 from both directions, and y steadily approaches 1. So, therefore, the limit of the function at this point is indeed 1. So this is correct. Now, at the point 0, some students might think that because there is a solid dot here, the limit is not 1. However, the limit has nothing to do with whether the point is defined or not. So we are only concerned with what value y approaches as x gets closer to a point. So as x gets closer to 0, we see that y steadily approaches 1. So the limit of the function at this point is indeed 1, which is also incorrect, which is also correct. So finally, at the point 3, we notice that as x approaches 3 from the left, y approaches 1. And while as x approaches 3 from the right, y remains at 0.5. Since the values approaches from the two directions are different, the limit at x equal to 3 does not exist. We use the notation D and E to represent this concept. Okay, so therefore, the correct answer for this question, which should be C. At this point, some students might wonder, must the limit always approach the same value from both directions? What if we only approaches from one direction, as in the case of point 3? So, how do we describe such a limit? Students who think of this are on the right track. And let's now introduce a new concept, one-side limits. So, if we consider the approach from the left side, this is called the left-hand limit. Denoted by the notation LIM with a small minus sign written above and to the right of the value C. So this means the left-hand limit. If we only consider the approach from the right side, it is called the right-hand limit, denoted by a small plus sign written above to the right of C. Using this notation, we can break down the two-side limits of a function into two one-sided limits, making it more convenient to describe the behavior of the function as it approaches a specific point. And with the notation for one-sided limits in place, let's now consider when a limit exists and when it does not exist. A limit exists if and only if it has left-hand and right-hand limits there, and these one-side limits are equal. So this statement might be a bit difficult to grasp at first, so let's examine its meaning through the following 4 graphs. Think about what's the limit at x equal to 2 are in each of the cases. So this graph is the most straightforward case, the limit which is clearly 3, and we can write as limit as x approaches 2, the limit which is 3. And let's go to the second one. Although there is a function value of 4 marked on this graph, as x approaches 2, y actually approaches 3. So, therefore, the limit is still 3. So we can write as x approaches 2, the limit is still 3. This graph illustrates that the limit of a function is independent of its actual value at the point. And let's go to the graph number 3. So in the third graph, we can see that as x approaches 2, y approaches 3 from the left and 4 from the right. Since the left-hand and right-hand limits are not equal, the limit does not exist. So, the last graph is the most misleading. Many students might think the limit at 2 is 3. But in reality, the limit does not exist. It is true that the left-hand limit at 2 is 3. So we can write as limit as x approaches 2, the left-hand limit, which is 3. However, when approaches 2 from the right, we observe that y does not approach a fixed value, but instead tends toward infinity. It's important to remember the definition of limit. As x approaches a point, y must approach a fixed value. Clearly, this condition is not met in this situation. Therefore, the limit at 2 does not exist. So, I believe these 4 graphs has helped clarify why both left-hand and right-hand limits must exist and be equal for the overall limit to exist. Now let's solidify this understanding with a few more examples. So, let's analyze the limit at 3 points, 1, 2, and 3. So at x equal to 1, the left-hand limit, which is 0, and the right-hand limit, which is 1. Since these are not equal, the limit does not exist. If you find it challenging to analyze the limit at x equal to 1, here's a helpful tip. Cover the right side of the graph with your hand to focus on the left-hand limit, and you'll see it getting approached to 0. Similarly, cover the left side to analyze the right-hand limit, which clearly approaches 1. And at x equal to 2, the limit which is 1. I believe everyone can now determine this confidently. At x equal to 3, the limit which is 2, which should also be straightforward to identify. Okay. And let's take a look at this example problem together. Feel free to pause for a few minutes to think it through. The correct answer, which is C. The left-hand limit at x equal to 2 is negative 1. And the function value at x equal to 2 is also negative 1. So, the first statement, it is correct. The left-hand and right-hand limit at x equal to 6 are both negative 1. So the second statement is also correct. The limit of the function at x equal to 6 is negative 1, but the function value at x equal to 6 is negative 3. So the third statement, it is incorrect. Therefore, only statement 1 and 2 are correct. So we're choosing the answer C. Let's take a look at this question together. I'll give you some time to think about it as well. So we'll analyze each limit one by one. Option A. The left-hand limit at x equal to 1 is 0. So it exists. So choice A is correct. For option B, the overall limit at x equal to 1 as approaches from both directions, it is 0. So it exists. Option C, the left-hand limit at x equal to 3 is 2. So it exists, which is 2. Option D, the overall limit at x equal to 3 when approaching from the right. The value of y tends towards negative infinity, meaning the right-hand limit does not exist. Therefore, the overall limit does not exist. Option E, the limit at x equal to 5 is approximately 4.5. So it exists. Thus, the correct answer is 4D. And finally, let's discuss a symbol for infinity. It's important to know that infinity is not a number, but a concept used to describe the behavior of functions. The first scenario where we can use infinity is with the variable x. For example, x can approach infinity. Consider the function x. Consider the function 1 over x. As x approaches positive infinity, y approaches 0. Therefore, the limit of y as x approaches infinity is 0. Similarly, as x approaches negative infinity in 1 over x, y also approaches 0. Thus, the limit of y as x approaches negative infinity is 0. This is the first context in which we can use the concept of infinity. The second scenario is that the result of a limit can also be infinity. For example, in the given function, as x approaches 1 from the left, the limit of y is negative infinity, while as x approaches 1 from the right, the limit of y is positive infinity. It's important to note that when a function tends towards infinity, the limit at that point does not exist. So, let's summarize the key points about the concept of limits. There are two main aspects we need to grasp. First, what is a limit? Try pausing for a few minutes and see if you can explain the definition in your own words. Second, under what condition does a limit exist? If you can answer this question confidently, it means you have a solid understanding of this topic. And finally, thank you for your listening.